In the last class, we learnt about the concept of rock mass tunnel support interaction analysis. I introduced you two curves. One was ground response curve and another was support reaction curve. And I explained you that how you can obtain these two curves with the help of few examples which were two-dimensional in nature. Today we will see how exactly this happens in the field with respect to a three-dimensional example of a tunnel construction. Let us try to see this. We have this three-dimensional condition and take a look at this figure and try to understand this carefully. I have taken a section XX, this one. The tunnel is advancing in this direction. So, there are various steps in the construction of the tunnel, such as step 1, step 2, step 3, 4 and 5. In the step 1, the tunnel face, which is this, has not yet reached to this section XX. And if you just cut it across this section XX, this is what that you are going to look for, that here it is all the rock mass is there and still at section XX there is no excavation. And that is the reason that the outline of probable excavation has been shown with the help of the dotted lines. Then the tunnel advances and you can see that you reach to step number 2, where the tunnel has advanced beyond this section XX. That means tunnel face, which is this face, is now beyond the section XX. And these vertical lines, these show the support system which have already been installed. So, here the tunnel has been advanced beyond the section XX, but the support system has not yet been installed here at this section. Come to the next step, which is step number 3. Tunnel has been advanced up to this point only, which was there in case of the step 2 as well. But now what is the difference between step 2 and step 3 is that now at section XX the support system has been installed. So, what you see in the cross section is, along with this tunnel excavated surface, you have here the support system which has already been installed here. Then in the step 4, tunnel has been further advanced. So, you see earlier it was up to this much, now it has been further advanced. So, what you will see at the cross section of this section XX is the same view, but what is the difference between step 3 and step 4 is that now the tunnel has been advanced further from the section XX. In case of the step 5, whatever was the excavation up to step 4, all the support systems have been installed up to that, plus the tunnel phase has been further advanced. So, these are the 5 steps that we are going to discuss in detail with reference to the generation of GRC and SRC. Before I go to that, we need to keep these few points in mind, that the tunnel is driven by drill and blast method. Support system is being installed after each mucking cycle. That means you advance the tunnel to some distance. Whatever is the muck material that is the result of this process of advancing the tunnel, it should be removed, and then the support system is installed in that excavated region. The third condition is, it is assumed that there exists the hydrostatic state of stress. This means that the horizontal as well as the vertical stresses, they are same. Now, let us try to understand the generation of GRC and SRC with respect to each of these steps in detail. So, I first take the step 1. So, here from the previous figure, I have just taken out the figure which corresponds to step 1. Once again, this is your XX section, and the tunnel face has not yet reached up to this section. That means it is here only. So, if you just take a cross section or take a section at XX and try to look in this direction, what you will see is the intact rock or the rock mass through which the tunnel is being excavated. So, in this case, the tunnel face has not yet reached the section XX, which is clear from this figure, which is defining the tunnel section under consideration. That means whatever are the tunnel sections that we are seeing in different steps in this particular form, they are the view of the tunnel about this section XX, which is constant with reference to the advancement of the tunnel. Then rock mass which is inside the proposed tunnel profile, that is this one. So, this is because it has not yet reached up to the section XX. So, this is shown as the dotted portion. So, whatever is the rock mass which is here inside this dotted section, this is in equilibrium with the rock mass which is surrounding the tunnel. That means that the rock mass which is here inside this portion is in equilibrium with whatever is outside here. And therefore, the internal support pressure which I am representing with Pi will be acting across the proposed excavation profile, that will be equal to the in situ stress P naught, and this is represented with the help of a point A, where we are trying to plot the radial support pressure versus the radial deformation. Now, please recollect our discussion of the last class where I explained you these concepts with the help of a two-dimensional situation for competent rock, for incompetent rocks as well. So, here the first point is going to be the point A, and here your Pi will be equal to P naught, which is the in situ state of stress. And since the rock mass has not been excavated at that section, and so obviously the radial deformation is going to be 0 in this case. Come to the step 2. So, this section XX remains the same. But now the tunnel face has been advanced beyond this section XX. So, how it will look like in this view? See here, so the material which was there inside this proposed excavated boundary, now this material has been removed and the tunnel has been advanced this much further the section XX. So, as I mentioned, tunnel face has been advanced beyond section XX. This material has been removed. So, this boundary becomes a stress-free boundary and therefore, the internal pressure Pi, it drops to 0. However, there is no collapse of the tunnel, no collapse of the tunnel. This radial deformation UR will be limited by the proximity of tunnel face, which provides a significant amount of restraint. See, this section XX is very much near to this face of the tunnel. So, because here you have the rock or the rock mass through which the excavation has to take place. So, this rock mass here provides the sufficient amount of restraint and therefore, the radial deformation UR is limited in this case. Now, in case if this restraint is not there, if it is not there, then what will happen is you will need to have some internal support pressure Pi in order to arrest the corresponding radial deformation, which is, say, you are at this point B, which I will show you in the next figure. But before that, you see here we take the same step and we have two portions of the tunnel. One would be the roof and another would be the side wall. That is, this is what is your roof and these are going to be your side walls. So, normally this support pressure for case of the roof is more than that for the side walls. This is due to the formation of wedge in the roof portion whose weight must be added to the support pressure in order to limit the stress induced displacement to its value. So, therefore, you get such type of situation that Pi for roof is always more than Pi of the side walls. So, in this case you see that here this will correspond to these 2 points B and C. Now, take a look here that the upper portion of the curve, that is this one, is the load deformation curve for the tunnel roof and the lower one is for the side wall. So, this point B corresponds to roof and point C corresponds to side wall, and you can see that if I take the pressure, then Pi corresponding to B is larger than Pi corresponding to C. Now, come to the step 3 where the tunnel has not been advanced further from the step 2, but what has been done is that whatever was advanced up to step 2, the support systems have been provided. So, at the section XX, which is this one, now the support has been installed, and therefore in this view you are seeing the support system as well. So this was the excavated periphery, the outer portion, and this is the support system. So what has been done in this step 3 is that tunnel has been mugged out and the steel sets are installed close to the face of advance. So this is the face of advance and the steel sets are provided close to this face of advance. Now at this stage the supports will not carry any load. So this will be represented by point D in the corresponding figure. I will take you there in a short while. Because no further deformation of the tunnel is taking place due to the installation of this support system which is in the vicinity of the tunnel face. In case of the rock mass not showing the time dependent deformation characteristic, these radial deformations of the tunnel will be still those which were defined by the points B and C of the step 2. Take a look here. This corresponding to this, you have the deformation here corresponding to this point D. So in case if there is no time dependent behavior of the rock or the rock mass, we are still here at these 2 points, that is B and C. And see, here at point D you will not need any support pressure. So here you see that it is starting from this point O. So support pressure here corresponding to the point D is going to be equal to 0. Now coming to the step 4, what has been done in this case is that beyond this section XX, the tunnel has further been advanced. So this usually tunnel is advanced about 1.5 times the tunnel diameters in one phase. So the same thing has been done here, that from the step 3 the tunnel face was advanced about 1.5 times the tunnel diameters beyond the section XX. Now the view here from this section XX will be same as it was there in case of step 3. So the restraint which was provided by the proximity of the tunnel face, it considerably reduced. See, earlier in step 3 the tunnel face advance was here. So this section XX was getting enough restraint because of the rock mass which was present in the vicinity of this tunnel face. But now since this face has been removed and this face has reached to this location, so the restraint which was there available at this section is no more available as the tunnel face has advanced to this particular location. So this causes further radial deformation of the tunnel side walls as well as the roofs. This is represented by curves CEG and BFH in this figure. See here, this is CEG, this one, and BFH. So this is your B, this point is F and it goes beyond that. So this is when there is no support system and the tunnel phase has been advanced. Now, in this case, the inward radial deformation or the convergence of the tunnel induces a load in the support system which acts like a stiff spring. So, the support pressure Pi available from the blocked steel sets that increases with the radial deformation of the tunnel. Take a look here that this is increasing from this point D in the manner this DEF. So, this is what is going to be the support reaction curve up to this much point. So, you see that how this GRC and SRC, they are plotted simultaneously. Coming to the next step, which is the step number 5, and in this case, beyond this section XX, the support system has been installed and the tunnel phase has been further advanced, and now this phase is much far than this section XX. So, this tunnel phase which is advanced far beyond the section XX and no longer provides any restraint for the rock mass at the section XX. So, whatever was the restraint because of this presence of this tunnel phase is no more available at the section XX, because this tunnel phase is much farther from the section XX. Now, here in this case the support system has been installed at the section XX, but assume a condition that if there is no support which has been installed, what will happen to the radial deformation of the tunnel? It will increase, and that will result into these lines EG and FH. See here, if the support system is not installed, it will further increase in this particular manner. For this is for the side wall and this one is for roof, like this. But then since we have installed the support system, so these have got restricted here with the help of these support reaction. But in the absence of the support, this ground reaction curve is going to follow this part EG and FH for side wall and for the roof respectively. Now, these side walls, the pressure required to limit further deformation drops to 0 at the point G, and in case of the side walls it will be stable since there is no remaining driving force to induce further deformation. On the other hand, the support required to limit the deformation of roof drops to minimum and then it begins to increase again. Take a look here that in case of the side wall, it follows this curve and becomes 0 at point G. So, that means here at point D, your internal support pressure, it becomes equal to 0. But in case of the roof, which is this curve, see, first it reduces and then it increases again. Now, what is the reason behind this kind of behavior? That first it is reducing for the roof portion and then it is increasing. So, this is because the downward displacement of the zone of the loosened rock in the roof layer, it causes additional rock to become loose. So, whatever was the mass in the vicinity of this excavated area, it gets loosened and it also causes additional rock to become loose, and the weight of this additional loose rock needs to be added to the required support pressure. Roof would collapse if no support had been installed in the tunnel. Therefore, the installation time of the support system in case of tunneling is very important consideration. So, here the section is XX. This tunnel face is much far than this XX. There is no restraint because of the presence of this tunnel face at this section XX. So, see here, finally what we will get for the roof portion, we will get this kind of the ground response curve, and in case of the side wall, here this is going to become equal to 0. Why? I just explained it to you. So, how to determine the slope of this curve? That is representing the support reaction curve. There are various types of support systems which are available, such as shotcrete lining, rock bolts, steel sets, or then you can have the combination of these. These support systems can be designed based upon the requirement of the particular project. Now, the stiffness of these support systems can be determined if we know the property of the, let us say we want to find out the stiffness of the shotcrete lining. So, if we know the property of this shotcrete lining, let us say its modulus is ES and the Poisson's ratio is nu s, and we know that the thickness of the shotcrete lining which is required is Ts. There are expressions which are used in order to determine the stiffness of this shotcrete lining. Similarly, in case if you have to go for the stiffness of these rock bolts, so what we need to know is again the properties of these rock bolts. Let us say ER, nu R. What is the length of the rock bolt that is required? So, if we know all these properties, the expressions are available in order to obtain the stiffness for the rock bolts. So, once we know the stiffness of these support systems, we can follow this support reaction curve and we can find out that what is the deformation that can be permitted and what is going to be the pressure which is being exerted on the support system in the roof as well as the side wall portion. So, this is what I wanted to discuss with you as far as the rock mass, tunnel support interaction analysis is concerned. So, this finishes our discussion on the chapter where we learnt one of the application area of the rock engineering, and that is tunneling. So, we learnt about the elastic analysis, elastoplastic analysis, and then the elastic analysis of the concrete lining, and then we saw the application of the stereographic projection in order to determine the shape and the size of the wedge which are formed in rock and the side walls of the tunnel, and then we learnt about the concept of rock mass tunnel support interaction analysis. Now, in the next class, we will take up the next application area of the rock engineering, which is the rock slope stability. Thank you very much.